Hello guys, in today's video we're gonna study a very fundamental concept in three different fields of mathematics, and that is topology, function analysis, and linear algebra. And that is the concept of quotient space. In this video I'm gonna go towards a linear algebra perspective for quotient spaces, and for the topological case we would leave it at some point later in time. So let's start our discussion of quotient spaces. So let X be a vector space and V is a proper subspace of X, so subspace. And now I define a term called coset. What is a coset? A coset is a set such that the set X plus V is defined. Maybe I should write it like this. So this coset is defined as X plus V for all values of small v belonging to capital V. Now, what just happened? So I have a vector space. I have a vector space. And I have a proper subspace V. So what I mean by coset is I have an X, and to X I add every element of V. So for all V belong to capital V, X plus V is equals to X plus V. So this is my definition of a coset. Now, what is a quotient space then? So let me write it here. A quotient space is the set of all cosets. So what I mean by X by V, so we would be using this notation of quotient space in the future videos also. So from now onwards I would call this thing as X quotient V. So X quotient V is, or as defined by X plus V. So now what you did next is, if you look at this diagram, and for every element of X you defined a coset. So this coset, now suppose this is X1 and this is X2 and this is X3. So for every element of my space X, you take this quantity, you take cosets. And if you think about it, this is not just one quantity, it is an entire set. It is an entire set of elements. So if I write, say, X1 plus V, I take X1 and I add it to every V belonging to capital V. So this is a set. Now similarly, for every element in my vector space capital X, I do the same operation. I take the set of all cosets. And this is what I call my quotient space. Now I define addition in my quotient space like this. So if you look at this formula, so having a quotient space does not satisfy my demand. I want to explore the structure of it. I want to assess whether it is a vector space or not, whether there is a norm associated there or not, and further properties. I start by defining the operation of addition and scalar multiplication in my quotient space by these formulas. So if I have a coset X plus V, and if I add it to Y plus V, is defined, defined to be X plus Y plus V. And similarly, in the case of scalar multiplication, I could write alpha times X plus V is equals to alpha X plus capital V. Now, once I have defined addition and scalar multiplication like this, I have to check that they are well defined. Now, well-defined is a very nebulous word used by mathematicians to mean a different thing depending upon the problem domain. So in our setup, what I mean by well-defined is that if you look here, you see that x1 plus capital V is equals to x2 plus capital V, and y1 plus capital V is equals to y2 plus capital V, and together these two imply that x1 plus y1 plus capital V is equals to x2 plus y2 plus capital V. Now I want this condition to be satisfied so that my addition operation becomes well defined. So if I want to define addition like this, then this should hold, else my operation of addition is not well defined. So in this step we check that, okay, is my addition well defined, and in order to define scalar multiplication like this condition should be checked, that okay, is x plus v is equals to y plus v, which implies that alpha x plus v is equals to alpha y plus v. So I do these two things to check that my addition and multiplication are well defined. That's the reason for doing these two steps. What I mean to say is I need to prove these 2 points. I need to prove them, these arguments, so that addition and multiplication becomes well defined. And in order to prove these two, I need to again need these propositions. So I need to first prove this fact, and I need to prove this. So what we are doing here is, in order to prove the well-definedness of the addition and multiplication operation, I need to prove that x plus v is equals to y plus v if and only if x minus y belongs to capital V. So I'll just prove one direction because the other direction is trivial. So you see, if I have x minus v and it belongs to capital V, I can write that x minus v here plus v plus capital V is equals to y plus some element v plus capital V, where v is equals to x minus y, which belongs to capital V. So therefore I can write this as simply y plus v. Now what's happening here is, this quantity y plus capital V is exactly equals to v, because when you add an element of a subspace to the space itself, it's all of that subspace. And the other fact that we need is that the cosets are either disjoint or identical. So that's the other fact that we need. So let us look at it again. In quotient space, we have a set of cosets. Okay, it's the set of all cosets such that this is how it is defined, that x quotient V is equals to x plus this set capital V, and we define addition in this way, we define scalar multiplication in this way, and in order to check that whether these two operations are well defined, we need to prove these equations, and we would need this particular identity. We need to prove this one in order to prove these two above. It's simple set theoretical arguments. And another fact that I need in order to give the structure is that the cosets are either disjoint or identical. So one quick remark that I would like to give about quotient spaces is, suppose this is my space capital V, which, like all subspaces, goes through the origin. So now the null element of my quotient space X quotient V would be, what do you guys think? Well, if you look at the addition operation, it was this thing. So suppose A plus something is equals to A. So X plus V plus something plus V is equals to X plus V, which implies that this something is just V. So capital V is the null element of my quotient space X quotient V and any element. However, X plus V is not a subspace. Why is it not a subspace? Because it does not have a zero element, and this is rather a coset. Now another idea I would like to put across is the norm in the case of quotient spaces. So if X is a norm space and V is closed, then X quotient V is a norm space, where the norm is defined as this infimum over capital V, norm of X minus V. Now this norm is in the quotient space, whereas this norm is in my space capital X. And similarly, if capital X is a Banach space, then X quotient V is also a Banach space. Finally, I would like to put across the idea of canonical projections. So basically, canonical projections are mappings from my space X to the quotient space. The mapping is given by this formula, and it takes me from X to the coset associated with it. It's very important. And one property of canonical projections is that they are continuous, which implies they are bounded. Why are they bounded? So if we take the norm of this pi x, which is given by this formula, so if pi x is defined like this, if I take norm on both sides, it becomes this. Now this was exactly equal to my norm in the quotient space. So if you look here, this is equals to the infimum over this. Now the infimum over V belong to capital V of this thing. Now what is the infimum over thing, which is, just look at it like this way. So X minus something is always a less than, of course, norm of X. It's as simple as that. One more idea I would like to put across is the norm of the projections is always less than or equal to 1. So this is less than or equal to norm of X. So the norm of the projection operator is less than or equal to 1. Pi x is less than or equal to 1. I hope. And so this brings us to the end of the video on quotient spaces and canonical projections. Wish to see you in the next video.